presentation on what this is all about. Rob.
I think Emery's last sentence was, we have many options. Today we will work our way through them together, and we will have a joint product. You have a clicker in your bag. We're going to use it. I'm going to describe the climate problem and the approach and a way of thinking about solutions. The two phrases you'll come away with are stabilization triangle and stabilization wedges. You'll do a little voting in the front end to get comfortable with your clickers. Then Roberta Otinsky will take over, and you will fill the stabilization triangle with 7 stabilization wedges collectively. You have no need to scribble lots of notes, because in that same canvas bag is a teacher's guide, and it has the information we'll be talking about and lots more. We also have a website at Princeton where you will find many useful resources, I hope, including the 2 papers that Steve Pacala and I wrote, the first in Science in 2004 and the second in Scientific American last September. We'll do a vote right off the bat to see who's here. You will vote 1, 2, 3, 4, 5, 6, or 7, depending on which category you'd like to locate yourself in. You don't have to tell the truth. You will vote when I say vote, and you can then keep changing your vote. Hard to see why you would, until we close the vote. Okay, so vote. In the bottom right-hand corner, I can watch the number of votes, and it's still going up pretty fast. So keep voting. No hurry. Take your time, get to understand the clicker, change your mind. Okay, I think we'll close the vote in 10 seconds. 8, 7, 6, 5, 4, 3, 2, 1, over. Very interesting. We had no idea what this would be. And we have a third people who make their living as teachers. I think that must be a tremendous achievement on the part of AAAS. So now let me start explaining the wedge concept. We start with the a single number that I'd like you to walk away from here remembering is that we now take 7 billion tons of carbon out of the ground each year, 7 billion tons, in the form of coal, oil, or gas. And virtually all of that is carbon dioxide in the atmosphere within a few months. A small amount goes into things like plastics and roads. But 7 billion tons of carbon. 50 years ago, it was less than a third of that, about 2 billion tons of carbon. By putting that part of the slide over to the left, I'm inducing you to think about the next 50 years. And 2 different questions. The first question is, if we have no particular interest in carbon over the next 50 years, what approximately are we likely to be emitting 50 years from now? You can imagine, take my word for it, there are thousands of papers on that subject, in various ways extrapolating from the past, imagining economic growth rates, population, technology, developing world, and so on. The other question is, if we take carbon seriously and worry about climate, as we surely are doing at this moment, given the talks we've just heard, what would we like carbon emissions to be in 50 years so that we should, in some sense, feel that we've accomplished much of what we needed to do? And again, thousands of papers, lots of disagreement about how strong is strong enough. What Pacala and I did 2 years ago was say, let's make this as simple as we possibly can to grab a hold of the subject. And this is the stabilization triangle. Although there are many estimates to what the carbon emissions would be in 50 years with no attention, it will approximately be pulling carbon out of the ground at 14 billion tons of carbon. And if we work very hard, maybe we can cut that in half and should feel pleased with ourselves doing so. There are, of course, by now, lots of critiques of this drawing. People saying we've underestimated how fast carbon will grow, and people saying we have to work harder than just to emit, and then we have to work harder than to allow ourselves to emit as much carbon as today, 50 years from now. We'll take these two lines because you can obviously modify the game by moving either of those lines. They're relatively easy to remember, and so onward. I would also note that if you try to translate that into consequences for the climate, the lower line followed by aggressive reductions in total emissions over the following 50 years might allow you to avoid doubling the pre-industrial carbon dioxide concentration, not by much. And the upper line, followed by 50 years of coming to our senses and getting on with leveling carbon emissions, followed by another 50 years after that, bringing down the carbon, might get you around triple the current pre-industrial concentration. So the binary choice is, in some sense, beating doubling versus accepting triple. The reason why this interim goal of emitting in 50 years no more carbon than today is not absurd are three, in my view. The world today has a terribly inefficient energy system. I always look at the ceiling of the room I'm speaking in after I say that. And unfortunately, in this country anyway, I'm rarely rewarded by modern lighting. Carbon emissions have just begun to be priced. Many of you know that the European energy system has now a carbon trading market. It's about to start its second phase. When the first phase didn't work as well as people thought it might, they went back and are trying to fix it rather than saying, well, forget it. We haven't got a carbon trading market in this country at this moment, but we're getting very close. And most of the 2055 physical plant is not yet built. This building, hard to know, but will it be here in 2055 or another one after it? But a lot of the construction of the power plants and the buildings of the world that will be present in 2055 is not there now. There is time, but we are building at a tremendous rate. So the second idea after the stabilization wedge, a triangle, is the stabilization wedge. I've taught you that it's 7 versus 14 billion tons of carbon 50 years from now. Break that into 7 equal pieces, a new physical unit for discussion of the subject, give it a name, the stabilization wedge. Can we fill the stabilization triangle with 7 stabilization wedges? What the rest of our period of time with you is about is learning what quantities of things are stabilization wedges. Well, a stabilization wedge, if it's a triangle, is 25 billion tons of carbon not emitted to the atmosphere. A typical price to think of for carbon savings might be $100 per ton of carbon, in which case it's a $2.5 trillion campaign or strategy. Big business, lots of activity, lots of people. And we're going to restrict ourselves to strategies we think are credibly going to give us the potential of a savings of 1 billion tons of carbon per year in 50 years. And moreover, somewhere in the world they are already commercial. We have gotten experience with the technology. It's not pie in the sky. We'll use our clickers to choose our favorite triangle. And people ask me, well, do you have your own strong favorites? And I have thought a lot about how to answer that. And as I've gotten to know the triangle, the wedges that one has as options, I realize all of them can be done badly and all of them can be done well. And that's what matters as much as which particular one, well, that matters most. And you'll have to assume in your own head as you vote that you've got some view of it's being done badly or well. So we have today separated these wedge concepts into 10 potential choices. So you will choose in each of your 7 wedges, for each of your 7 slots, one of these 10. You can use one more than once, and so forth. There are 2 under the energy efficiency and conservation category, 2 under a fossil fuel category, 1 under a nuclear category, and 5 under renewables and biostorage. Let's start with the efficiency wedges. Amory has made a very strong case that we can do a lot of the job with energy efficiency, which we break here into two broad categories, one which is primarily technological and one which is primarily social and behavioral. And the question about urban sprawl brought out that very issue just a few minutes ago. Energy efficiency can be in many sectors, particularly in transport and in buildings, and also, however, in how efficient our power plants are, and energy conservation or behavioral change can certainly also occur in all sectors. Oh, I'm sorry, I want to go back one. I will show you in 4 instances here, because now that I know we're 1/3 teachers, all the more reason to do so, what students can do in each of these 4 categories. This very week, my students at Princeton are doing an energy diary. I've told them to think about the energy use in their own dormitories or perhaps back at home, and to go into some part of this in detail and to make it a carbon footprint, not just an energy footprint. It has to start with collecting data. Whether you learn where the meter is in your own home or the school has a meter, you start with the data and you start going on from there, and you learn and you learn and you learn. The efficient use of fuels, a number which is worth remembering, my second one, I guess, is that we put a ton of carbon in the air when we drive a 30-mile-a-gallon car 10,000 miles a year. That's a reference ton of carbon a year. There will be something like 2 billion vehicles in the world in 2050, about 3 times today. If they are 30-mile-a-gallon vehicles getting 10,000 miles a year, that will put 2 billion tons of carbon into the atmosphere. So one way to get a wedge is if it would have been a 30-mile-a-gallon car, it's a 60-mile-a-gallon car on average at that time, also going 10,000 miles a year. Another way to get a wedge is to have the 30-mile-a-gallon cars, but go 5,000 miles a year, because we've done something a lot about public transport, about city distance of commute, and about telecommuting, and so on. And of course, if you have 2 billion 60-mile-a-gallon cars going 5,000 miles a year, that's a wedge and a half. What are the obstacles? Love of power under the hood and urban sprawl are the 2 I decided to mention here. Many of us are not aware of what a large fraction of our electricity is being used in buildings today. In this country, it's close to 3/4. We use a certain amount of electricity in factories, but in residential and commercial buildings, we are using electricity for things we're completely aware of. Lighting, various kinds of motors for refrigerators and air conditioning, water heating in many instances. A wedge would probably be knocking 1/4 off of that total in the buildings. We have problems which lead to buildings like this one and any other one I'm likely to talk in the next 6 months. A divided responsibility between the building owner and the building and the builder and the tenant, and attention to first costs in an exaggerated way. They're all solutions, but we have had this list for 30 years. So I've told you 7 billion tons of carbon go to the atmosphere each year, and there are about nearly 7 billion of us. What does that mean? The world average is 1 ton of carbon going to the atmosphere per year per person. Well, I've just begun to get into understanding better than I used to what a ton of carbon a year is in our own world. We Americans, on average, are putting 5 tons of carbon per year into the atmosphere, each of us. And those of us in this room are probably above that average. Where is a ton of carbon per year going? Well, the first is my 10,000-mile, 30-mile-a-gallon car. Cut it in half in each of those 2 ways. Third is approximately as much carbon goes into the atmosphere for a mile of flying in commercial aircraft, if you take your share of the number of passengers in the plane, versus driving a car on your own. There's no other passenger. So 10,000 miles of flying is about a ton of carbon. Heating your home, natural gas, average climate like my own in New Jersey, average sized house, no terrific attention to energy efficiency as Amory has done, you'll put about a ton of carbon into the atmosphere. If it's a natural gas, or probably oil-heated home. Lighting, another opportunity. And electricity in homes, another opportunity, because it 1,600-watt bulbs, and you can think of those equivalent appliances, running quarter of the time, will put a ton of carbon into the atmosphere if it's a coal-powered area of the country, like, say, Ohio or Illinois. To answer that one for any particular place, you have to know the carbon intensity of your home electricity, something I would argue that schools can pay attention to. So, another vote. We'd like you to vote now which of these 5 campaigns of cut by half you would least like to participate in. Double your car's fuel economy is 1. Cut the miles you drive in half is 2. Cut the miles you fly in half is 3. Reduce the energy used to heat your home by half. Insulated windows, furnaces improved, and so on is 4. Reduce your home electricity use by half is 5. Vote. Which one would you least like to join as a campaign? Knock on people's doors to encourage them to participate in. Be part of it, actively, aggressively, productively. About to cross the 400 point. Getting close. 15 seconds of mine. 10, 6, 4, 2, 1. Okay. This is a group which thinks it can fly less. I'm very interested in that answer. This is a group that doesn't want to give up its flying more than it doesn't want to give up its driving. I can tell you we played this in New Jersey, and it was completely lopsided with vote number 2 winning. Okay, we want to do one more, because I want to get you used to the idea that your vote is going to depend on a group's vote. So now we're going to vote again on your second choice. Given that we're going to take reducing flying off the table, because you so much don't want to reduce your flying. We'll pick one of the remaining 4 as the one that you're next least want to give up. Vote. Fast. All right, we're going to stop in 15 seconds. 10, 6, 4, 3, 2, 1, over. Okay, as expected, you're giving up those vehicles. Somebody said in an earlier talk that it was a personal choice how much you would use telecommuting and video conference. It's also a tremendous technical challenge. This is the IT capital of the world. If we're not using a video conference so as not to fly in a business, what I call unwanted travel, if we're not doing that, the technologies are, in many instances, not good enough for us to pass up that trip, and they'll get better. And one of the most important ways in which the IT community can contribute to climate change is to make wonderful connections to displace the unwanted travel with photons and electrons. All right, let's drive on. Surveying the wedges, and I need to move faster. In the case of fossil energy, carbon capture and storage is the new boy on the block. It says we can possibly keep burning coal, oil, and gas, but the CO2 is redirected and doesn't go to the atmosphere. It can come in connection with coal power, for example, conceivably coal to hydrogen, especially when hydrogen is used in industrial purposes, and also if coal is being used for fuels without making transport fuels, for example. There's a great deal of CO2 that can be captured. I'm personally very interested in this technology. It's going to get more and more attention. The public doesn't know it very well. We haven't had much conversation about it, but I hope you know something about it here. The second, fuel switching, means that you would use natural gas instead of coal. About half as much carbon goes into the atmosphere at a power plant that uses natural gas for the same amount of electricity as at a coal plant. The student exercise focusing on carbon capture and storage that I'm thinking of is to learn about the below ground wherever you are. Most of us know very little about what happens directly down from where we are, except in religion school. So let me say a couple of comments about the fossil fuel wedges. There's a rush to coal, as I mentioned. This is the urgency of climate mitigation is greater than we imagined 5 years ago because of this rush to coal. The building of hundreds of coal plants, 100 apparently gigawatts in China last year, an amazing amount. All sorts of parts of this country now trying to permit coal plants of the old kind without any carbon capture whatsoever. My sense is we've got to stop that as almost priority number one. And as far as imagining what it looks like, the CO2 would go below ground somewhere near the power plant into a porous formation. It would fill a lot of space down there. But we do know how to move fluids in the oil and gas industry. Those industries would be given a new job. And some of them can see lots of big bucks down that way. And if they can do it well, they will certainly help. Then the N word. I will use the N word. There can be nuclear power as part of this solution. It's one of the good examples of doing it badly or well. For a student exercise, there are 100 plants in this country. Where's the one nearest you? Who owns it? How does it work? All kinds of issues that you can think of. And then in terms of scale, another number to learn is if we have 700 modern 1,000 megawatt coal plants, they will put about a billion tons of carbon into the atmosphere in a year. So substituting for 700 modern coal plants is a wedge. You can do that with nuclear power, kilowatt for kilowatt, with 700 nuclear plants. And we're talking globally. The world has 350 of those plants, so another double current amount instead of coal is a wedge, and phasing out nuclear power is minus half a wedge. Let's drive on. 5 categories of renewables. Wind and solar electricity. Lots of ways of making electricity renewably. Solar is itself several things at once, as I'll say in a moment. Wind can be used to make hydrogen instead of electricity. One interesting calculation is if you want to avoid carbon emissions, the wind could displace coal for power, or it could make hydrogen to displace gasoline. It turns out that in most situations, if you have both options, you want to go for the coal power plant first. Biofuels, much to be said. I'm going to have to leave all that for your imaginations. You can grow biofuels for vehicles. There are many interesting ideas. There's also some serious wrong turns when you use as much gasoline to make, or petroleum or coal, to make the biofuel as you end up saving later on. And biostorage, more carbon in soils, more carbon in forests by letting them grow, not cutting them down. There are wedges in that direction. Just briefly, the photovoltaic power can come both in decentralized and in centralized forms. As you all know, the challenges are the cost. It's the most costly of all the things we've discussed today so far, but costs are coming down. And the intermittency, which can be solved in a variety of ways, including by sharing the grid with fossil and renewable energy. And wind electricity, let's put a number on here, 1 million 2-megawatt windmills. That's approximately the wattage in the picture. 1 million 2-megawatt windmills displacing coal is a wedge, taking into account the intermittency of the wind. The challenges include the sense of intrusiveness that so many people seem to feel. We've got to get to the point where we find them pretty in order to move forward. Now it's Roberta's turn.
All right, so what we've done at Princeton is we've developed a game, which is an interactive small group activity to explore the stabilization wedges concept. And what we do in the game is this triangle has 7 equal pieces, and that's analogous in the graph that we saw that Rob presented at the beginning, the doubling versus the flat path. These 7 colored wood pieces are, at least in the original version, they're made out of wood, represent the 7 wedges of carbon emissions that need to be cut out in the next 50 years to get us on a flat path toward avoiding dramatic climate change. So the Wedges game has been played in many forms. It was actually developed as an icebreaker activity for our annual meeting where we have our sponsors, BP and Ford, come and work with our researchers and learn about our new findings. And one of our co-directors, the other co-director who's not here, Steve Socolow, made giant wooden game boards in his basement over Christmas for this icebreaker. So that's up in the top left there. It turned out to be a really successful exercise. So the word leaked out, and people from all over started asking us if we could facilitate workshops. We've done it in large group sessions, never as big as this. Down at the bottom, I did it at a climate conference in Melbourne for about 130 people. There are policymakers and people from industry, lots of adult professionals we've used it with. And then the Department of Energy has used it at their National Youth Science Camp. That was high school students. And it seemed to work really well for them, too. So we're really happy to be able to share it with you today. The version that we do, you have in your bag, you don't need to look at it now, but you have a teacher guide to the game, and in it is a lesson plan. This is designed to be an activity to do over 2 to 3 days, where the students get to learn about the concept, because as you saw, it's sort of a fire hose of information coming at you in half an hour of all these different technologies, but there's information about the different technologies in here. And then we would also, in the way we've done it in our workshops, has been to divide people up into groups. So we advise the students be broken up into groups, and that way they get to, each group builds a stabilization triangle out of 7 wedges. So they negotiate and have to come to consensus, and more importantly, they have to defend their solutions to the group at the end, to a class. We won't obviously be able to do that today, to divide up into small groups. So we're just going to give you a flavor of what the Wedges game is like, and then afterwards we're also going to be able to meet with people who are interested about actually executing the game in their classrooms. So what we're going to do today, the wedges are divided into 4 categories. In the guide, you'll actually find that there are 15, and if you count them up, there are 15 here, but the clicker's only allowed 10 options, so we condensed them down. And the categories we're going to be voting on, Rob told you about before. We've gone over efficiency in great detail. Increased efficiency is going to be, there's one selection, but within that, you should think about the 3 different categories that we've calculated wedges are available in transport, in buildings, and electricity production. The doubling of the efficiency of all cars, for all passenger vehicles, for example, is a wedge in transport. Cutting building emissions by 25%, or increasing electricity production from 40 to 60%. Those would all be examples of wedge activities, the emission savings that are available. I should also mention these are what our researchers have calculated are wedges, that we know that the capacity, where we believe the capacity is out there to scale up these technologies in 50 years to take care of 1 billion tons of carbon emissions. But there are also others, so this is not an exhaustive list. But moving on to the fossil fuel-based strategies, carbon capture and storage, conservation, I forgot, reduced mileage is also available in the passenger vehicles sector, as Rob described, also in freight and transport. Fossil fuel-based strategies, carbon capture and storage, that's available for coal or natural gas-based electricity, also hydrogen production for hydrogen fuels and syn fuels. The scale of a wedge would be using carbon capture and storage at about 800 large coal electric plants, about scaling up hydrogen production by about 10 times relative to what we have today, or using carbon capture and storage, or CCS, at about 180 coal syn fuels plants. Fuel switching, as we talked about, Rob touched on briefly, it's switching from coal to natural gas. Requires about 4 times the natural gas that's used for electricity today, and about this amount of natural gas used for all purposes, just for building a wedge worth of natural gas-fired capacity to displace coal. For nuclear energy, nuclear electricity, Rob mentioned that we'll have to triple nuclear capacity. Renewables and biostorage, we have a group of 6, 7, 8, 9, 10 there. Wind electricity means 2 million large windmills. Solar electricity means a 2,000 kilometer square array, which is about the size of New Jersey. So keep that in mind. Wind hydrogen is double the amount of windmills as for electricity. It's 4 million large windmills. Biofuels means scaling up world ethanol production by about 30 times relative to today, which also means planting biofuels over a really large area, about the size of India. So that's, we want you to impress upon you that none of these is an easy effort. Wedges are monumental tasks. And then finally, biostorage, forests and soils. If we halted deforestation in the next 50 years, that would be a wedge. Also planting forests over an area of the contiguous United States, that would be one wedge. Or using conservation practices on all agricultural soils worldwide would be one wedge. So there are lots of tools available to us. So what we're going to do now is we're going to be voting on the particular strategies that you think should be added to a wedge next. And I want to impress upon you, think as your students would, not only in terms of what's your favorite, but what you think in designing strategy to go forward, what you think should be added to their portfolio. So I've got my instructions for voting here. We're going to use the clickers, and we're going to use them 7 times. So we will fill in, you've got an example of the stabilization triangle on there on the right. We'll fill in the first wedge, and you'll see what the answer is. And then based on that result, we're going to keep voting. You can continue to vote for your favorite. You can adapt, but we want you to consider what's already in the triangle before we vote. So you can use the same strategy more than once. You can use it twice if you think the capacity is there. If you think we could get more than one wedge out of efficiency in transport, then feel free. So I think that's all our instructions. So now we're going to have our vote on voting in your 4 categories. So do we have the slide up here? Yes? Okay, so vote now. Just vote once. Yes, just vote once now. We're going to vote for the wedge that you want to see added to the portfolio next. So vote now. We're going to vote one time for the first wedge, and then when we'll see the result of that. Okay? So everyone, the vote's coming in. Looks like we've got most. Everybody will give another one of Rob's 15 seconds. 15, 10. I'll give it longer because it's the first vote. So 5, 4, 3, 2, 1. All right, so let's see what came up. Our first wedge. We've got to wonder about the influence of Amory Lovins on this particular vote. So increased efficiency by a lot. This usually comes up in the games. It's a popular strategy. So now we've got one wedge of increased efficiency. Now that could mean really intense efforts in say, doubling the fuel efficiency of passenger vehicles, or less intense efforts across transport, buildings, and efficiency. So given that we have now one wedge through increased efficiency and the scale of the magnitude of the effort that takes, we're going to vote now on our second wedge. Remember, you can use the same strategy if you think there's more capacity there, or you can use a different strategy if you think if that's what you prefer. So, ready? We're going to vote now. right, we've got 15, 10, 5, 4, 3, 2, 1. All right, see what we've got this time. Okay. Well, this is kind of a surprise. It's so still very heavy in what we have as our efficiency categories in the yellow. We're both increased efficiency and reduced mileage, very close. So we'll go with another wedge of increased efficiency. So now we've for example, doubled the fuel efficiency of all passenger vehicles, increased building efficiency by 25%. These are really big efforts to be thinking about. So we're going to follow this with a vote on our third wedge. We have 2 wedges of increased efficiency. All right. So considering that we already have 2, we've got 5 more to go. There's plenty of room for all sorts of tools. And we're going to move on to our third vote. So vote now. We're getting faster and faster. That's good. All right, looks like almost everybody's done. So we'll do 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's see what the result is. All right. So people are beginning to fade off the increased efficiency a little bit. I thought we might have our first all-yellow efficiency triangle today, but that's good. We had 7. We can fill it in that way if we need to. So wonderful. So now we're in reduced mileage. So wonderful. Even though people think it's a difficult effort, we think we have the capacity. Oh, so I'm sorry. Solar electricity. Anne's ahead of me. Yes, solar electricity. So we've backed off. Okay, so solar electricity means a PV area that's around the size of New Jersey. This could be a big array. It could be big arrays scattered, or it can be on rooftops or other surfaces. So, so solar electricity. Great. All right. Read them more carefully the next time. So now that we've got solar, this is our third wedge. We'll now vote for our fourth wedge. Vote now. So we're getting close. We'll do 15, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so we're done with voting. All righty, wind electricity, if I'm reading this correctly this time. Okay. So wind electricity, remember, means putting up about 2 million 1-megawatt windmills. We're an area of about 3% of the U.S., so we're going to have a lot of windmills, but they can be distributed all over the world. They don't have to be all in one place, clearly. And yeah, so there we are, wind electricity. Now, given how much wind we already have, you can choose to do that again. We can vote for that again. You can, if you think there's the capacity, if we have capacity for more than a few, the 2 million windmills, or we can choose another strategy. So vote now. All right, we'll go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The numbers are dropping on the voting. I hope everybody's keeping up. Okay, so let's see what the result is. Okay. Back to reduced mileage. Finally, you're getting to realize what a scale of effort this is. And that, so I'm very proud of us for getting that into the triangle. So remember, this could be in flying, driving, or freight. So we can do it in not just in passenger vehicles, but we can do it through increased transport, telecommuting, as Rob was suggesting. So we're on to 3 yellow wedges now and 2 green wedges. So this is when it starts to get interesting. We're going to move on to our 6th vote. So everyone vote now. Okay, we'll say in 5, 4, 3, 2, 1. See what our result is. Okay, fuel switching. Blue wedge for getting more colorful. So this will mean using natural gas to displace coal electricity at 1,600 coal plants. 1,400. And it'll need an amount of natural gas about equal to what we use for all purposes today. So, all right, so fuel switching. You can't see the color that well, but so now we've got 3 yellow, 2 green, and 1 blue. So now we're going to vote for our final wedge. So vote now. Alrighty, so we'll go to 5, 4, 3, 2, 1, and we'll close the voting. All right, storage and forests and soils. Yeah, it's amazing how the distribution changes over time. These are a lot of hard choices to be made. So forests and soils, if it were forests, it would be halting deforestation in the next 50 years, planting new forests over an area of about the size of the contiguous United States, or in soils, using conservation practices on all agricultural soils worldwide. So, so here's our wedge. We ended up with 3 yellows, let's see, 1 blue and 3 greens. Yes, so you can see what the purpose of the game is to convince you that we need a portfolio of technologies. As Margaret Lyman said before, there is no silver bullet. All of these are going to be really big efforts, and that's the main purpose of the goal is to also convince you that there's no right answer. Every time we play this game, it changes. So, so that's the game. You've got your game packets. Remember, feedback, we'd love to have it. We want you to both use this game. We hope you'll be able to use it. We've also hope, though, that you'll be able to adapt it and send back to us materials that you've developed that are more appropriate for high school or younger audiences. And we also want to convey to you that this is part of a larger effort for your students. There are groups around the world in industry and government and at all levels thinking about strategies and building their own wedge portfolios. This is an example that appeared in Al Gore's movie, An Inconvenient Truth. It's from the Natural Resources Defense Council, and it's suggesting a wedges strategy that for just the U.S. So the numbers are a little smaller because we only produce 25% of the emissions, but the colors don't match, unfortunately. But if you can read the first, can we work on here? No. The first 4 blocks, they're not exactly equal in size, so they're not wedges. The first 4 are efficiency, so not so different from us. Renewables are the sort of mustardy color, and then carbon capture and storage. which we didn't pick in our session. So one of the take-home messages is that your students are going to be participating in something that's a real exercise that's going on around the world. And maybe that's one more. People are beginning to recognize that it's not a time for just sitting and saying we can't do it anymore. There's been a transition to now is the time to get something accomplished. And your students can be a part of this debate if you equip them to. And the Wedges debate, the Wedges game, we think is a really good tool to do this. And we're hoping that teachers can lead the way to getting this all the Wedges implemented, because your students will be the taxpayers, the scientists and engineers of tomorrow. Thank you.
Well, thank you very much, Rob and Roberta and Anne, for that extraordinary, entertaining and instructive display. We now have a few minutes for questions. Again, you can line up at the microphones, and the first one is over there. They can be directed to Rob or Roberta, or let them choose. Yes.
Great, I'll let you choose. It's a great game. It's really great to see it, not just for students, but even adults. And I guess along those lines, I'm wondering if for university level and people like those in this room, if you thought of a more advanced version where it could have 14 wedges, so a number of other technologies and mechanisms could be considered. For example, building conservation. I feel like students especially can think about thermostats and different conservation opportunities in buildings, and this sort of doesn't suggest to them that opportunity. Similarly, it seems like you could probably have a wedge for our consumption choices and emissions that come from use of industrial complexes. So I'm wondering if you're thinking about that.
Oh, yeah. I think it's wonderful. It has been used in university settings in essentially the same form that is in your packets, but I don't know how much Rob's used it in his courses, and it's a wonderful opportunity to really sit down and figure out, these carbon emissions, and it's a really good exercise. So I think it would be wonderful as a tool especially for a longer term study, to look at it as sort of a unit.
One quick addition or amendment to your question. The game in your packet has 15 choices. Buildings and transport efficiency are actually separated. You can also obviously add your own choices, but we dropped from 15 to 10 yesterday when we discovered the clickers could only handle 10.
I'm sorry, no follow-ups, and we're going to have to ask questioners to keep their questions brief so we can get a number in. Over here.
Okay, first of all, I want to thank you for the game. I think it really helped me to see what I'm personally willing to give up, and then also how we as a community, what we're willing to do as a community, not just as individuals. But I have a comment that was that's sort of related to this, is that when we're looking at fuel transfer, replacing coal with natural gas, and this hasn't been mentioned at all while I've been here, so it's directed to you, but I'm not meaning it necessarily for you, is that natural gas, the extraction of natural gas is destroying aquifers in the Midwest, on American Indian lands, and American Indian tribes have had to give up so much in order to fuel our way of life, uranium, all that. So
can I cut in? I mean, yeah. I would put that as a very good example of doing it well or doing it badly for any one of these things. Doing it badly is the kind of impacts you're talking about.
Okay, thank you.
Over on the other side.
So having played this game in the group, I'm still not sure what taking these votes is supposed to measure, and whether then whatever it is supposed to measure, whether taking a winner-take-all plurality vote any number of times with only one item being the winner of each vote measures whatever it is we're supposed to be measuring all that accurately.
Sounds like there's social science research projects by the hundreds right here.
I would say it's adapted for this large group. Clearly, it's not an ideal setting. What we do in the small groups is what we're really interested is not in a particular outcome. What we want students to discover is that through reading about the wedges, that they are such a big effort that there will need to be a combination of strategies, and that they can't be a particular advocate for one strategy, and to learn to compare the different different sizes of the wedge, what the effort is for in terms of windmills versus coal plants, et cetera. So we really don't have an outcome other that they explore and come to that realization. And in the game, what we advise doing is have the students report back and be able to defend their solutions. And I think that is really where they learn. When you just vote like this, you just pick your favorite, and you don't necessarily have to have any consequence. But if you had to stand up in front of the room of 1,500 people and say why I picked solar electricity, for example, then that would have some ramifications. Also, in our workshops originally, we had judges come in who were really subjective, or played a subjective role. They'd represent the interest of different climate stakeholders, and then the participants also got the idea that it's not just about the physical feasibility, but also the political, economic, and environmental consequences and how they'll be accepted by the public. So there are those sorts of lessons to be learned from it too.
Let me just add to that. I played the game the first time it was offered at Princeton because I'm on the advisory board that was meeting there to their project, and one of the most useful aspects of it was discussing within groups how to put together a portfolio of pieces and how the portfolio would then be defended in front of the whole group. Here in the middle.
I'm worried about those 150 new coal-fired power plants that are planned for this country. There's no legislation yet to capture or store the carbon. In view of all that, is it reasonable for citizens to ask that any new planning phase coal plant capture and store its carbon beginning with day one of operations?
I believe it is reasonable to ask that.
Next one here.
My question also concerns coal. If 50% of the energy in our country is derived from coal, what advantage would it be to use the Fischer-Tropsch process from Rentec or Sasol in order to do that? And why aren't we have the political will to make coal more energy efficient using processes like that?
The question is, can we use coal more efficiently by using it for liquids rather than electricity? We do use it. Neither is an efficient process from a carbon perspective. If we make liquids from coal, we will put twice as much carbon in the atmosphere per mile of driving than if we get those liquids from crude oil. The good news, moderately good news, is that second carbon can be captured at the transfer plant with carbon capture and storage, at the conversion plant with carbon capture and storage, at which point it would be no worse than petroleum. But it's not an efficient process. It's making the best of a relatively bad situation. I'm very concerned that we'll go down the road of coal to liquids without carbon capture and storage, and that is about the worst thing one can get going in the climate picture.
Over here now.
Thanks. I wanted to know how many of the remaining people are teachers and how many of those teachers actually teach about global warming in their classrooms.
Wow. Look around.
Great.
Teachers?
Does the teachers teach it?
And teachers who teach global warming. Yeah. All right. Right on. Thanks.
Terrific. Back here.
I realize that this would be a daunting task, but is there any way that you could add cost, or capital cost at least, to the wedges? Because it's very easy for us to vote, but we don't know what the cost is.
I think, as Roberta was indicating, we're imagining multi-class units dealing with these subjects, putting the economics in. People are trying to do that. In my own view, all of these are relatively competitive with each other, with a modest carbon price of approximately $100 a ton of carbon, the price I used in one of my slides, $30 a ton of CO2. They all get into play. So that adds 25 cents to a gallon of gasoline. It changes the coal to natural gas competition. It makes carbon dioxide capture about marginally financially viable. It brings a lot of this into play. The sort of price I think we need to get to relatively quickly, along with other policies to go through the transitions.
Okay, this will be the last question.
Thank you. Given Amory's comments on the leverage available in downstream efficiencies, I'm just dying to know how many wedges Amory filled with efficiency, or thinks could be. 7. 7. All right.
He clearly didn't influence.